Here we want to show that the set U1, U2, V1, V2 is a basis for R2 if and only if U1 plus U2x and V1 plus V2x is a basis for P1. And let's just quickly remember, P1 is the set of polynomials of the form A0 plus A1x, where A, I are real numbers. So let's go ahead and prove it. The first thing to remember is that the dimension of R2 equals 2, and the dimension of P1 equals 2. So since we know the dimension and the dimension matches with the number of vectors in our set, we either need to show that our set is linearly independent or that our set spans the space. We do not need to show both. So in order to show these sets are bases, it suffices to show that U1 and U2, V1, V2 is linearly independent if and only if the set U1 plus U2x and V1 plus V2x is linearly independent. Let's call this set S1 and this set S2. So S1 is linearly independent, means that when I take a linear combination of the vectors U1, U2, and V1, V2, so A and B are real numbers, and equate that to the zero vector in R2, then necessarily it means that A equals 0 and B equals 0. Or equivalently, if I just rewrite this, I get AU1 plus BV1 and AU2 plus BV2 equals the zero vector. So this is an equivalent statement. And this is equivalent to saying that each of the coordinates is equal to 0. Let's just make a dividing line here. So what does it mean for S2 to be linearly independent? That means that if I take a linear combination of U1 plus U2x and V1 plus V2x and equate them to equal 0, then that necessarily means that A equals 0 and B equals 0. Again, this is equivalent just by rewriting to AU1 plus BV1 plus AU2 plus BV2x equaling 0. And by equating coefficients, that means AU1 plus BV1 equals 0 and AU2 plus BV2 equals 0. Note then, if S1 is linearly independent, so that's an equivalent statement, A, B are real numbers, then that's equivalent to showing that each of these equations is satisfied. But these are the exact same equations you get when you look at the vectors in S2, and working our way back by the equivalences, we see that S2 is linearly independent. Similarly, if we start off by assuming S2 is linearly independent, then we necessarily get that S1 is linearly independent. So then S1 is a basis for R2 if and only if S1 is linearly independent, and we've shown that this is equivalent to S2 being linearly independent, which means that S2 is a basis